Welcome to everybody. I'm Isabella Mastreni from University of Verona, and I'm going to present a joint work with Vincenzo Arcieri and Nea Zaffanella from University of Parma. And this work is about static analysis by APLAS interpretation. And APLAS interpretation is a well-known framework for providing answers about programs by computing abstract semantics, and static analysis usually is a technique for automatizing this process. And what we propose here is just a technique, an approach for improving precision of this kind of answers, of this kind of analysis. So let's start by introducing very briefly and easily in a very simplified way, the framework of abstract interpretation. Abstract interpretation is a framework, as I said, for providing abstract approximated answers about programs. And it is based on a formal framework where we provide how we can provide relations between the concrete data of programs, on which programs will compute, and an approximated data on that we use for overcoming the undecidability problem, well-known problems of program semantics. So the starting idea is just to provide how we move from the concrete to the abstract world. And so let's suppose to have programs computing, for instance, on integers. The concrete domain of values is the set of all the collections of values that can be computed during the program execution. On the abstract side, we just decide which properties we want to observe precisely. In this case, suppose to want to observe only whether a variable is odd or even during the computation. So the framework of abstract interpretation is based on, first of all, on an abstraction function associating with each collection of values the best property in the abstract world that will approximate this information. So if we have a set of all even numbers, then the property we can observe is precisely to be even. So, for example, for 10 and 100 is approximated in even. Similarly, if we have a set of only odd numbers, then we approximate it as the property odd. If we have a set of numbers which are both even or odd, then we cannot say anything about the parity of our collection, and therefore we say, I don't know, the top of the abstract domain. So this is the empty set is abstracted to the bottom, and this is the abstraction function. So the abstraction associates each collection of concrete values with the best approximation in the abstract world. Then we have a concretization function which associates each abstract property with the meaning of this property in the concrete world. So, for example, even means the set of all the even numbers. The same thing can be done. This is a very easy and toy example, but we have much more complicated and complex domains. For example, intervals, where we abstract the range of sets. So, for example, if we have a set of values for 10 and 100, we approximate it in the range from 4 to 100, and so on. So this is the context of abstract interpretation, which is used to abstract data and therefore to abstract computation. Static analysis is just a way of automatizing this computation, abstract computation on this data. We introduce this static analysis again very briefly, but on a toy example, which will be our running example. We have this program with a loop and a branch. When we perform a static analysis, the first thing to do is just to build the control flow graph. And after, once we have our control flow graph, we have to associate with each program point an equation, which allows us to derive, which is the abstract information that we have at that program point. So, for example, when we compute the information in the program point x2, it is the join of the information coming from x1, the information coming, which is even, which is a constant value, the information coming from x4, which is just the value of x4 plus an even number, the abstraction of 2, and the join of the information coming from x5, which is the value of x at x5, plus an even number, which is the abstraction of 10. This is a very easy situation, and the idea is just to derive by linear iteration on these equations the information holding at each of these program points. And if you compute this information on this easy set of even, what we obtain is that at each program point, apart from x1, all the numbers are even. So if we have property, we need to answer some questions about the program concerning the parity of values, we know that the variable x is always even. We can see how it works on a very on the domain of intervals, which is more significant, and we can see that we start from the bottom, just for starting the linear iteration fixed point computation. And at the first iteration, what we see is that we have the initial assignment to x, which is 0, and we propagate to the reachable states precisely this information that the x is precisely 0. Then, by computing the different iteration, we just increase the range of values that x can have in each program point. And this is happen in the same way until we reach the value 50, which activate the false branch of the x3 guard, and then we start increasing again the values. And when we reach 100, then we can activate the false branch of x2, and we reach the fixed point. As we can see, in this case, is very easy example. We reach a fixed point. In this interval domain, it may happen that we diverge, also in the abstract case. But anyway, we reach it in 32 steps, which may be, if we scale, it may be quite a lot. So the idea is just, the fact is just that we need some way to improve this computation. In particular, graphically, we see that what we have done is just a computation of this iteration function f, which is our semantics, and our aim is to reach a fixed point. The problem is that in the computation, also in the abstract computation, sometimes this iteration may be too long or even infinite. So the solution exists in literature is just to accelerate this computation in order to reach a post-fixed point approximating the original fixed point. This is widening. It's called widening. How it works is just a new operation that accelerates the process, and since it induces a loss of precision, it's not necessary to perform widening in all the program points, but only in some chosen ones. In particular, it is sufficient to have one widening point at in each loop. So, for example, in this simple case, we decide to take x3, and therefore we perform the widening set at least upper bound when we compute the x3 value. So let's compute again the fixed point, but with the widening. What we observe that the first iteration is precisely as before, because we just have a finite value which is propagated. But then, still already in the second step of iteration, we have that at point x3, the computation of the widening leads to the unlimited bound, since we have that the widening works by observing that the upper bound is increasing, and when it is increasing, then it is directly led to the unlimited, to plus infinite. So as you can see at x3, we lost any information. We only know that the value is positive, and this information is then propagated all over on the whole program. And we reach the fixed point after 4 points. So before it was 32, now 4, but we have a relevant loss of precision. As you can see, in 4 points, we lost the upper bound. So this is the situation. We reach the post-fixed point, which may add a huge loss of precision. And this loss of precision, it may be quite unacceptable. And therefore, in the literature, we have several techniques for regaining some precision. In particular, one of these that we consider is narrowing. So it's a technique for refining the solution that we have reached by widening. Let's see, again, in the example, we keep the same widening point, and in this case, x3 is computed by considering this widening. This widening starts from the post-fixed point that we reached and starts refining the result. So we start from the fixed point we reached, And then the refinement just simply observes that a point where we have an unlimited bound is now in the following step with a definite bound, which is 99, because we have a guard that check whether it is greater or not than 10. And so the narrowing in this case keeps the finite definite bound, so 99. And then we propagate again this information. And what we obtain is that after 2 steps of narrowing, we reach precisely the right fixed point. Here, this is a very easy example just to show how it works. And it is like a lucky example because we reach precisely the original fixed point, but in general, this is not what it happens. We have a loss of precision that is we are unable to completely regain. So, anyway, this process introduces in general a huge amount of imprecision, and in order to mitigate this loss of precision, in literature there are lots of solutions and also advanced solutions that allows to reduce the loss of precision due to widening in particular. So we have widening with thresholds, widening with hints, or there are techniques for intervening the widening and the ascending and descending phases, so the widening and the narrowing phases. There are other techniques that restarts the widening and narrowing phases, each time from a different perturbation of the fixed points and so on. But all these solutions use a fixed upside domain. So they start with a fixed domain, and they keep this domain, the domain where of the information we want to observe, fixed, and only changes the way they compute the information. So this is the situation. We have an upside domain. On this domain, we compute the widening process, and on the same domain, we compute the narrowing for regaining some information. What we observe in our approach is that these 2 phases are completely unrelated. I mean, we just reach a fixed point, and from that fixed point, we apply a refining process for regaining information. But they are not really connected one from the other. So the idea here is just to change the descending phase, considering a more concrete domain. Because since in the descending chain phase, we can control the complexity, since we can stop the computation of the narrowing whenever we reach the unacceptable degree of precision. In this way, by taking a more concrete domain in the descending phase, we can have a more concrete, so more precise domain where to compute information, and at the same time, we believe that we can really tune and control efficiency. So the idea is just to connect these 2 domains by a transfer function that simply takes the post-fixed point we reached and transfer it in the new, more concrete domain. And then on this value, we compute the narrowing process. What we observe is that independently from the choice, if we take a more concrete, a concretization of A, of the original domain, we always have a more concrete answer. And the idea in this work, the main task of our approach is just to provide a process allowing to have a more concrete answer, more precise answer, because the main task is just to have it while controlling the efficiency, because, as I said before, in the concrete, in the descending phase, the widening can be controlled by stopping the refining process whenever we reach a good level of degree of precision. So let's see. And moreover, another thing is that this approach is completely orthogonal with the existing in literature techniques. So it can be indeed combined with other techniques, existing techniques. So let's see again on the example. We consider as widening and as narrowing a standard narrowing holding for all the domains, which is the greatest lower bound, which is the most concrete possible, the most precise possible narrowing that keeps soundness and that can be therefore stopped, as I said, whenever we reach a fixed amount of iterations, like in our example, which is 2, or whenever we reach a acceptable degree of precision. Moreover, we consider as a concrete domain, more concrete domain for the descending phase, the power set domain of intervals, which is the collection of all the sets, all the finite sets of intervals. So we take the post-fixed point we reached, which is in the first column, by the widening, and we transfer it in the power set domain of intervals. So we take the singletons. At this point, we can perform the narrowing, and it performs by considering as least upper bound and this more concrete domain just almost the union with some adjustment, and as greatest lower bound the pointwise intersection. Also, the operations between intervals is a pointwise operation, so it is just a combination of all the operations on the sets contained in this power set. And without entering details, what we obtain is that after 2 iterations, which is the amount of iteration we fixed, as we can see at point x3, we have a really most concrete domain, which is really sound, and it is not convex. You can see that I have holes, and this makes it more precise than the solution we found before. Graphically, in order to see the relation between this approach, in this slide you can see precisely the original approach existing in literature, so in the same interval domain. We compute on the left the widening computation on the program, and we reach a post-fixed point, which is 0 plus infinite. And on the same post-fixed point, we computed the narrowing on intervals that provides the value, which is in this case a fixed point, but in general is a post-fixed point. If we change the interval domain with the power set of intervals, then we have to transfer the fixed point we reached in the singleton, so in the power set domain, and we compute from this element the narrowing, so the greatest lower bound iteration, refining this solution and obtaining this solution, which is depicted in blue. And we can observe that indeed it is really most concrete than the original fixed point solution. So it should be clear that our approach has as main task the one of refining, so providing a more precise solution while controlling efficiency, because the hardest part is the fixed point iteration, and we leave that on an abstract domain, which is simpler and less, where it is simpler to compute the values and more scalable. While we move the refining process on a more concrete domain, but this is possible because in the descending phase, we can tune the precision or the complexity of the computation by stopping the computation when we reach a fixed threshold. This technique has been also implemented in the used analyzer is Pagaye, and the benchmarks are the one distributed with this analyzer. And the abstract domains considered are the box, which is the intervals, and octagons from Apron, and polynomial, polyedra, and polyedra set, the power set of domains of polyedra from PP-Lite. And we have considered all the combinations between ascending and descending phases with these domains. In the comparison, the idea of this table is just to consider that we want to fix a baseline from which to start to understand where we can indeed improve the analysis. So the first line is the baseline, where we compare the whole computation ascending and descending phase on intervals and the whole computation on polyedra set. And we observe that they provide the same solution, almost the same precision, in the 38% of cases. It means that only in the remaining percentage we can indeed improve something. And in particular, what the second line tells us that we improve with the decouple, the ascending and descending phases for the 47% of cases. We have an answer which is more concrete for the domain 2 with respect to the domain 1. So indeed, we improved precision for 50% of cases. And the third line has just compare for the descending and ascending phase decoupled with the more concrete domain, just to understand that indeed we are almost like for the 60% of case, the more concrete domains. But in the more concrete, we have also the ascending phase made on the more concrete domains, so with a less efficient computation. The same kind of comparison have been made for octagons and the polyhedral set. And again, the results are positive because our approach improves the precision for the 44% of cases, while keeping the same precision for this almost 70% of cases. And the last one is the comparison between polyhedra and polyhedral set. And again, in this case, our approach increases the precision for 35% of cases, while keeping for the 86% of cases the same precision as the more concrete one. So concluding, in this work we provide an approach for exploiting the widening and the narrowing process. So this combination of two different processes, one for computing a fixed point, even if it is less precise, and one for refining this solution, in order to improve the general precision of the analysis, and at the same time controlling efficiency, because, as I said before, in the narrowing phase, the descending phase, we can use a narrowing guaranteeing soundness, like the greatest lower bound, and therefore we can stop whenever we decide to stop. So we have at each point we can stop and by keeping soundness, but we decide when the amount of resources that we want to use for this computation. Clearly, there are still work to do. There are some limitations, in particular for the benchmark we used for testing. So it is really a preliminary evaluation. We believe that these benchmarks are not adequate for example, understanding the real impact on efficiency and in particular on scalability. So we need to find some benchmarks which are more specific for understanding whether we are really impacting on the efficiency of this analysis. So this is the main limitation of this evaluation in particular. As future works, we are considering mainly two directions. First of all, we think that it's not necessary just to apply the technique uniformly on the whole program, but we could find with some techniques, for example, also quite advanced, like machine learning, in which parts of the programs this decoupling can be really impactful, can be really useful, in order to apply only when it is necessary. And the other direction is to drive decoupling. I mean, precision is well known that is strongly connected with a theoretical property, which is completeness. And there is a huge amount of literature about transformations related with the completeness, to drive completeness. And therefore, it can be really interesting to understand if you can use theoretical properties, theoretical proof on the program, just to drive which is the concretization we have to use. In the examples we just guessed, we just decided which more concrete domain to use, but maybe completeness can allows us to find a good concretization, which is suitable for the kind of precision we want to reach. That's all.
Thanks, Isabella. Now we've got questions. Here we are.
Thanks for talking very much about the tutorial beginning. Do you have any properties of the transfer function? I mean, I'm guessing it's not.
It's a concretization.
It's a real concretization. It's a Galois connection.
Yeah, because the idea is just to choose a concretization of A as the descending domain.
Okay, so we can compose the Galois connection.
Exactly.
In the middle. So that's really cool. That's another one. Yeah. Okay. Is there any overhead for using this decoupling? So is some analysis slower? So for example, if you use the identity transfer function, then I just recall the original case. So maybe I can do as well as the usual case, but somehow they can do better. So it's in fact always use this
Well,
decoupling?
there's not really an overhead. I mean, it's just you have to this transfer function depends on the complexity of this computation here. But indeed, since it is a concretization, it's just a mapping on a different representation of the same object. Indeed,
Okay,
because the concretization just takes the meaning in a different. So, like the interval was just a singleton, and in general, it's just a change of representation. And then on that representation, we can compute the new function. I don't know if I answered.
So the takeaway is I'm not paying any price, but you don't have the evidence to say I definitely benefit a lot from it.
Yeah, I don't pay any price in the transfer, and then I can control the
Thank you.
execution.
Hi.
Hi.
How do you know what domain to choose? What concrete domain to choose to actually benefit? Heuristics or?
I mean, at this point, we just guessed. I mean, a domain for which we know we have a good implementation and which is indeed more concrete. The last point is just the idea to have some techniques for driving the choice. So since the precision is indeed related, as I said, with the completeness, there exist in literature some transformers refining domains for inducing completeness. So the idea is just to combine these two ideas, the more theoretical one and this more practical, just to understand if we can drive, we can formally prove which is the best concretization we can use for that particular program, if it is necessary. But in general, it depends on the program. I mean, the same domain can be precise for a program, but imprecise for another one. So it depends if this effort is useful. I mean, and
Are there any more questions?
Actually, I have a question. I was wondering, how do you encode the domain for the narrowing only? So it's like a domain, because I know about the reverse product, which is what you use when you want to combine different domains. So I was wondering if you just put like the box, so the interval domain and the power set interval domain in a brand new domain, or did like a reverse product between the interval domain with a useless narrowing and the power set domain with only the narrowing, which is encoded.
yeah, we compute them separately. So first, in the first domain, we compute the widening, then we change function and we start computing on the, so we don't need to combine or to make a complete new one.
Okay.
It's just two different phases, which are indeed independent. So we exploit this independency, just not with the non-necessity of combining.
Okay.
Thanks. So you, based on this, what you said, future work, right? You said that I can choose different domains for each loop, right? So the domains can define the loop, and the narrowing, the descending domain, that only operates on both fixed points. You never take into account the fact that you're only working on a limited collection of your semantic domain in the descending chain. So kind of relying on the fact that
we didn't consider it yet.
But you think
It can be nice. It can be interesting. Yes.
Do you have any intuition? I mean, this is a very difficult question. But any intuition how that might benefit you?
I mean, perhaps by understanding for fixing perhaps the degree of precision we want to reach. I mean, start having some information, fixing some information on the starting point. We probably can know in advance which is the precision that we can reach. But I mean, it's just.
Thank you. That's good. Good stuff.
Any more? The next week is set up then. Thank you very much.
Thank you.